Hello, my name is Sean Zilberdrut. I am an undergraduate studying electrical engineering at the University of North Carolina, Charlotte. I want to thank you for giving me the opportunity to speak to you about my research at NCC. Alright, so the world is really facing an interesting phase of energy technology currently. We made a lot of strides towards making solar and wind more viable options of energy sources than they were in their infancy. In addition, we've also seen that power grid operations have greatly improved, giving us greater access to data. We're calling these smart grids now. We're even coming up with new grid topologies. We're calling these microgrids, where we can share energy between houses or between businesses. Now, if you've ever read Reinventing Fire, you might recognize this figure. It shows four possible futures to how our future power production and transmission will look like. I want to focus in on the fourth quadrant labeled Transform. This is the ideal future in that our grid can supply continuous and reliable power from only renewable sources. Now, it's clear that the world is adopting more and more renewable technologies, such as solar and wind. As you can see from here, we're seeing, if we adopt this transform model, we're going to see a large increase in rooftops PV, and it's key to see that we adjust our distribution grids to this growth so that we can realize this transformative future. But now currently our distribution grids simply cannot handle these large penetration of PV. So what I'm going to show you here is a possible solution to this. So here, this is an example of a PV array output over the course of a day. I use this output profile in the simulations involved in our research. Anyone who's studied photovoltaics will recognize this as sort of curve, where this bell-shaped curve where it peaks around midday. That's where we have the greatest intensity of sun. Now, in the real world, you will have clouds overhead blocking out the sun momentarily, and that causes even further variation. So this is an ideal case. So what this does on the rest of our system, this is a diagram of bus voltage. This is any general bus on a system. That varying power output can cause our voltage to also follow that same pattern. So our homes in the U.S., they run on 120 volts, and you do have some variation as to its lowest and its highest limit. Once you venture outside, you might have a temporary outage of some sorts. Because the voltage isn't within that range. So it's important that we keep the voltage at a steady, constant rate so that we have reliable power coming to our homes and businesses. Now, currently the utility would schedule generators or operate capacitor banks to increase or adjust this voltage so that it's nice and constant and that our loads are operating healthily. But we're going to see here that there might be an alternative solution. And what I want to show you here is that we're going to term this voltage variation throughout the day from its maximum to its minimum peak as long-term dynamics of the voltage. Now I'm going to come back to a old fundamental of circuits theory. Take a general system such as this. And I'm going to come and look at bus M as my reference. I can turn this system, looking from bus M, into an equivalent system with an equivalent voltage and equivalent impedance, where I have now greater control, greater observability over what I can see in terms of voltage and current into this bus, rather than looking at this complex system over here. And what we call this is Thevenin's theorem. So now the voltage and current is over here should be the same that I see in our original system. Now, what I'm getting at here is that I can take this Thevenin impedance and this Thevenin voltage and vary it in some way so that I can maximize or optimize my voltage and current at this bus M. And I'll see that same change back here. Now, how do I change these parameters? Well, I can change this through changing the topology of a system. So take this as an example 9-bus test system that I used in simulating the relationship between the changing topology and the long-term dynamics, that voltage variation. So I took bus 9 as a reference, and I took these 3 switches through all their possible combinations, 8 in all, and for each configuration, I looked at what is the resulting voltage at this bus 9. As you can see, for each configuration, you kind of see an improvement from the first configuration where no switches are closed to the last where all 3 switches are closed. Now with these configurations, I am allowing loops. So with our current distribution grids, this would not work due to its radial nature and its original design. So if we can transform the distribution grid, turning it into these mix of microgrids, then we can help clean energy power our future and make it a more viable option to power our homes and businesses. Thank you very much.